Hello everyone. In this session, we'll deal with chapter 3, which is very interesting and very important for design point of view. In chapter 3, which is physics used in HVAC. And you know this, without these concepts, you cannot think to deal with this designing part for this HVAC, especially for the load calculation. And when we deal with the fluid mechanics or this say ducting, piping, all these concepts is required. So in chapter 3, physics used in HVAC, we'll start with the heat. And you see, if you're dealing with the air conditioning, so air conditioning, the first parameter, adding or removing the heat, right? So it must to understand what is heat. So we'll start with the term heat. Then we'll discuss about the temperature and the temperature scales. Then we'll also talk about this sensible and latent heat. And we'll deal with this vapor compression cycle, refrigerants, loss of thermodynamics, units and conversion, all this topic in chapter 3, and which is very basic and very important for design point of view. If you know this concept we can use at the time of designing, especially this sensible heat, latent heat, temperature scales, units conversion are very important. Okay, and we'll deal with the vapor compression cycle, which is required at the time of chapter 4 when we deal with the classification of machines, because in all commercial and residential units, you'll find vapor compression cycle only, right from this window to chill water chillers. Okay, so this is very important. So I know this is very basic, but we cannot ignore this because without this, it's difficult to deal with the load calculation or the designing part. So let me proceed. So here, the first term you can find is the heat. And you see, we are dealing with the air conditioning, adding or removing the heat as to maintain the required temperature for summer or winter. So first of all, you must know what is heat. And as a mechanical or as an engineer, I believe you already know the heat, but my responsibility is to explain this quickly because as I said, this course, what we design is from basic to the advanced level. So you know about this terms and terminology, but in this session, we'll try to understand this terms and terminology for application point of view. Okay, not just theoretical. We'll try to understand for application point of view. Then only you can involve in the designing because concept is very important. So here on screen, heat is what? In short, I can say heat is a form of energy. And temperature is what? Temperature and heat both are same or different?
Different.
Yes, heat is a
temperature is different. Yes, sir.
so heat is a form of energy and temperature is the intensity of that energy.
Yes,
okay,
sir.
so with the temperature, we can find out the rate of heat transfer, but the content of heat, the content of that energy is a heat. Okay, or else the heat we can also call in technical term as enthalpy, right? Heat content of the body. So what exactly heat? You can find out here on screen. Heat is a form of energy transfer that occur between the substance with a different temperature. And you know this, whenever there is a temperature difference, then only the heat will transfer. Na? If the temperature, if it is same in both the bodies, and if it is physically connected, that will attain what? Thermal equilibrium and will not transfer the heat. So heat will transfer only when there is a temperature difference. If there is no temperature difference, there will no heat transfer because both the body will attain thermal equilibrium. And this term also will use at the time of load calculation, especially at the time of learning heat gain through partition, floor and ceiling, because heat gain through partition means between the two rooms. If the two rooms with the same temperature, it means there will be no heat transfer. Okay, so just I'm trying to relate these terms with the load calculation so that when we deal with the load calculation, this will be useful or this will be helpful for us. Next, heat can be transferred through conduction, convection and radiation. So I believe you know what is conduction, convection, radiation. If you are electrical, even electrical engineers also know these basics. But still, if you have confusion, don't worry. We have a topic in the next page only about this conduction, convection, and radiation. So the heat can be transferred with the different modes. This we can call as a different modes of heat transfer. It can be conduction, convection, or radiation. And it's a fundamental concept in thermodynamics. And you know what is thermodynamics? It's responsible for changing the temperature of object and can be measured in units like BTU. So as an engineer, you know calorie, joules, kilojoules, etc. What you learn in the engineering. But this term BTU may be new for many. Those who are new to this field. Those who already in the field, they know this term is very commonly used in actual practice. BTU. BTU is what? In short, we used to call BTU. It's a British thermal unit, right? So what is BTU and how to understand this? That also we'll discuss. Let me proceed. So you see, heat always transfer from high temperature to, the low temperature. No? According to which law? This heat transfer from high temperature to lower temperature. According to which law or which thermodynamic law?
First law of thermodynamics.
Any more? Okay, it's according to second law. Anyhow, we have this laws of thermodynamics also, first and second law. In this chapter 3 only, we'll discuss before dealing with the vapor compression cycle. Okay, because this basics very, very important. So try to understand the applications out of this. And you see this heat transfer from high temperature to low temperature, this applicable at the time of learning vapor compression cycle, because in vapor compression cycle, you'll find condenser and evaporator. So in condenser, heat will reject, and in evaporator, heat will extract. And because of this nature of the heat only. Okay. So by nature, heat will always flow from high temperature to the low temperature, right? Everyone aware of this. We'll discuss more about this in second law of thermodynamics in chapter 3 only. Next, as I said, the unit of heat is a BTU commonly in actual practice. It can be joules, it can be calories, but most commonly in actual practice. This is actual practice means I'm talking about for this load calculation point of view. We're using this term BTU. So if you talk about the units of measurement, you know, SI units or English also known as imperial. Commonly, we are using this two measurement system in actual practice, SI, and metric is a part of SI, and English or imperial. So this BTU is a unit belongs to English system, and in SI we can use joules. Okay. So what is exactly BTU? We'll try to understand, because at the time of load calculation, when we extract the heat gain through all the possible sources, the end result is going to be in BTU per hour. So we must know how much BTU per hour is adding for a particular space. Then only we can able to select the required capacity cooling unit. Or in case of heating also, we must know at what rate the heat is rejecting from the space. Again, that we are calculating in terms of BTU if we are dealing with the English system. So what exactly BTU is? In case of conversion, you see 1 joule equal to 0.000948 BTU, or 1 BTU in terms of joules is 1055.06 joules. This is the values, but what exactly the BTU? That we'll try to understand now. Okay, so you see, even this calories also will be used, which is also a part of English, not commonly, but most commonly in English system, you'll find BTU. So 1 calorie in terms of joules also is given the conversion. So the conversion you need to memorize, that will use at the download calculation. And we have a separate topic for conversions also in this chapter 3. Okay, next, we'll try to understand what is BTU, and it can be asked in interview also, very basic interview question. And even for the load calculation also, as I said. So you see, BTU stands for British thermal units. It's a unit measured for energy, nothing but heat energy. And 1 BTU is defined, this is important. You see, 1 BTU is defined as the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at constant pressure. Once again, 1 BTU is defined as the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at constant pressure. So what do you think? BTU is a large amount of heat or a limited amount? You see, 1 pound of water means 1 kg. In terms of pound is what? 2.2 pounds. So I can say half liter of water, say 1 pound. And in order to increase 1 degree Fahrenheit of heat, Fahrenheit means again it's a unit for temperature in English system. In case of SI, we are using degree centigrade. So what is degree centigrade, Fahrenheit? That also you'll find in the same chapter. But as an engineer, you know these terms, Fahrenheit or centigrade or Kelvin, etc. So what do you think? This 1 BTU is a large amount of heat or just a limited?
Limited.
Yeah, because you see, 1 BTU is a heat energy which is required to increase 1 degree Fahrenheit of what? 1 pound of water. Okay, so it's a very limited amount of heat energy at constant pressure. So here, this example will help you. You see, this is very simple. 1 pound of water in a container, 1 pound of water in this container here, and initial temperature, say 50 degree Fahrenheit, for example. And after this, I'm going to add the heat. And how much heat? Say 1 BTU. So when you add 1 BTU of heat energy in this container, which is of capacity 1 pound of water, so what will happen? The temperature will increase from 50 to 51 degree Fahrenheit. Okay. So 1 BTU of heat energy is responsible to increase 1 degree Fahrenheit of 1 pound of water. That's it. So in English system, we can say the specific heat of water is what? Yes, online? 1. Because specific heat is what? Specific heat na, for unit volume to raise 1 degree Fahrenheit. That is a specific heat. So here 1 BTU is what? 1 BTU is a specific heat for water to increase 1 degree Fahrenheit for 1 pound of water. So here specificness, so we are considering a unit volume and for 1 degree Fahrenheit. So remember, this will use at the time of calculation. So specific heat of water in English system is 1, right? And it's a very, very basic and important for interview point of view. So you must memorize this definition. You see, 1 BTU is the amount of heat energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at constant pressure. Next, so we'll deal with one example. Here you see, simple example. So you know this 1 degree, to increase 1 degree Fahrenheit for 1 pound of water, 1 BTU is required. Now in this example, you see initial temperature of water says 70 degree Fahrenheit, 72 degree Fahrenheit. I'm interested to increase this to 82 degree Fahrenheit. Means how much I'm interested to increase? 10 degree Fahrenheit, right? Because the difference is 72 and 82 is 10. Na? Of what? For what? For 10 pound of water. So what do you think? How many BTUs of heat energy is required? We have 4 options. 1,
100.
10, 100 or 1000.
100.
Yes, online? I got the
100.
answer 100. What about other participants?
100.
So 100 is the correct. Why?
Because mass is 10 pounds.
Right. And even the degree also it's 10. So 10 into 10 is what? 100 BTUs are required. In case if I consider 1 pound, then 10 will be the correct answer. Okay. But if here the content is a 10 pound, na? So that's the reason 100 BTUs are required. Very simple. But try to understand the concept, because this will use at the time of load calculation. Because the time of load calculation, when we deal with the heat gain through wall, heat gain through partition, floor, ceiling, ventilation, etc., that we are going to calculate in terms of BTU per hour. So you can understand, this 1000, 2000, 3000, 5000 BTUs per hour heat is entering from outside to inside through this wall or through this glass, etc. Okay. So that's the reason this basic is very, very important. Hope you got the idea online about this BTU, British Thermal Unit. Next, temperature, very, very important. So at the beginning of this session, we discussed temperature and heat both are not same, right? So heat is what? Is the energy. And the intensity of energy is a temperature. So you see, this is important. It's a measure of thermal activity or intensity in a body, not the heat content, not the thermal energy. The thermal energy or the heat content is a heat, but the intensity of that. So anyhow, you see, it's a measure of thermal activity or intensity in a body, or it's a degree of hotness or coldness of a given system. Means, and you can relate this point, as the temperature increases, what will happen to the rate of heat transfer? Increases, right? And as the temperature decreases, the rate of heat transfer also decreases. So temperature is not a heat, because with the temperature you cannot find out the quantity of that heat. Getting a point? And this activity is depend on the movement of molecules. Okay, so you'll get some idea. You see with this picture, everyone aware of this: solid, liquid, and gases. And you know this, in solid, the molecules are closely packed, na? And in liquid, somewhat loose, and in gases, further. And with this, you can try to understand the nature of the temperature. You see, solid means I'm talking about ice, liquid is of water, and gas a vapor. So what do you think? In which case you will find higher temperature? Solid or liquid or gas?
Yes.
Gas. And in which case you will find lower temperature? Solid, right? So now you can relate, as the temperature increases, the movement of molecule also increases, na? You see, here the activity depends on the movement of molecule. So the movement of molecule start vibrating. So in solid, the temperature is less. That's the reason the molecule can be closely packed. The movement, because the movement is less, right? And as the temperature increases, the movement increases. So it required more space for the movement. That's the reason you'll find more space in liquid and further in gas. So I think you are getting my point. Means you can able to understand the nature of this temperature. So as the temperature increases, the intensity of that heat increases, or the movement of molecules or the velocity of molecule increases, or in other words, the kinetic movement of that molecule increases as the temperature increases. Got the idea online? And with this, you see the rate of heat transfer also increases. As the temperature increases, the movement of molecule increases. So when the hot body come into contact with the cold body, the intensity of this hot body is high. So when it touch, so the movement of molecule, the velocity is high, so it can quickly transfer. Getting a point online? So can you able to catch this? You see, all these basics, as I said, will help you in load calculation, in manual load calculation. And manual load calculation, we are supposed to deal for the concept. And with that concept only, you can deal with the software load calculation. Okay, so all are interrelated. So please don't ignore this concept. This is very, very important. Now, further, if you talk about the temperature, the temperature can be measured in different scales now. So if you talk about English system, we are dealing with the degree Fahrenheit. If you're dealing with the, say, SI metric, we are using the centigrade, or we can use this Kelvin in metric. So we'll try to understand this temperature scales, because this will help at the time of conversion. Because in actual practice, your consultant may use English system or metric system, or many times this conversion is required. Okay, so for conversion, the type of this scales and the difference between the scales all is required. So you'll find different temperature scales, but commonly in actual practice, degree Fahrenheit, degree centigrade, and Kelvin. Okay, we are not calling degree Kelvin. Remember, we used to call Kelvin only. And Kelvin is an absolute scale. So what exactly? Here, this picture will help you to understand the clear idea. Let me zoom out. Interesting. Here I'm considering sample as water in this for this scale. So here Kelvin to centigrade, then Fahrenheit to centigrade. So first Kelvin. So you see, this is absolute zero. Absolute zero means theoretically the moment of the molecule is a minimum. That condition we can call as a absolute zero. And just now we discussed the temperature is the intensity of heat, nothing but the movement of molecules. If the movement of molecule is zero, or theoretically say zero, that we can call as absolute zero, that we are considering in Kelvin. And remember this value 273. 273 means in centigrade we are considering 0 degree centigrade, and this 373, say round off, I'm just taking round off because in application design we are taking the round off value. That much two digit or 4-digit accuracy is not required. 0 digit is enough. So 373 degree, sorry, my mistake, 373 Kelvin is 100 degree centigrade. And this 0 degree centigrade is what? Freezing, or the melting point of water, no? Freezing point of ice or a melting point of water. Okay, and this 100 degree centigrade is what? The boiling point of water, or the condenser. This condensing point means if you add the heat, water to vapor, or if you extract the heat, vapor to water. Okay, so this conditions, everyone aware of this. 0 degrees of freezing point, 100 degrees of boiling point in degree centigrade. If you talk about Kelvin, 273 and 373. Okay, because Kelvin here is the absolute zero, and you see minus 273. And this, if you want to convert this centigrade, suppose to Kelvin, so we have this conversion 273, but you see Kelvin is not commonly used in this HVAC industry. Most commonly you'll find this Fahrenheit and centigrade. So we'll discuss about this, and this is important. So remember this point, 32 degree Fahrenheit is nothing but 0 degree centigrade. Is what? Freezing point of water, or the melting point of water. At this level, to avoid confusion, I'm considering say freezing point of water. Next, 212 degree Fahrenheit is what? 100 degree centigrade. Remember these values, we'll use at the time of conversion. In the next page, you'll find the formulas also for centigrade to Fahrenheit and Fahrenheit to centigrade with respect to temperature and with respect to temperature difference. So we'll discuss what is temperature and temperature difference. But one more point here. So quickly you see 0 degree centigrade equal to 32 degree Fahrenheit, and 100 degree centigrade equal to 212 degree Fahrenheit. Apart from this, you can notice one more fact here. You see at minus 40 degree, the difference of both the scale is 0. You see, minus 40 degree Fahrenheit equal to minus 40 degree centigrade. This question may ask in interview. in the written exam. If any company conduct a written exam, you can expect this question, very basic. So remember, at minus 40, the difference of both the scale will be 0. But again, you see here in above or below, you can see the difference. Here minus 22 is minus 30, minus 58 is minus 50 here. But at minus 40, the scale difference is 0. Okay, so remember this point will be useful in the calculation also. Next, we'll talk about the temperature scales. So this already discussed, now heat and temperature both are not same, but interrelated. So heat is the energy and the temperature is the intensity of that energy. Okay, next, this formula is very important. Memorize this because at the time of load calculation also this will use, because in actual practice you must know both these systems, because some consultant use English system, some will use the metric system. So or some consultant or many consultant use the mixed system. In actual practice, you see this term CFM commonly used, which is belongs to English system for this ducting side, but the duct fabrication and duct designing in that will use which is a metric. So we'll talk about that conversion. We'll talk about the units in this chapter 3 only. Just I'm trying to give the idea so that you must you must memorize this conversion. This is very important. So remember, C equal to F minus 32 by 1.8. So here F minus 32. So why we are subtracting 32 to get centigrade? Because this is 0 and this is 32 now. So that this is the first reason. So this centigrade, if you want to convert this Fahrenheit to centigrade, the first factor is you need to subtract this 32, because this is 0, this is 32. No confusion, no? For example, you see this is 30, this is 86. But okay, don't follow this. Just at this level 0.32, because here you cannot understand this 0.32. So first point, why we are subtracting this 32 in the formula, I think there is no confusion. Now the question is why we are considering this 1.8. Remember,
so in the centigrade scale there is 100 division, but in Fahrenheit scale there is 180 division.
Very good. You see here, this is 0, this is 32, this is 100, and this is 212. So 0 to 100, this is 100 divisions. But 32 to 212, how many divisions? 180.
180.
So it means one division of the centigrade is nearly 1.8 of Fahrenheit. This is one division. This is what? 1.8. Suppose this is 0.8. Getting my point? So one division of centigrade is equal to 1.8 division of Fahrenheit. That's the reason in the formula we are using this 1.8 to get dividing with 1.8 to get the result in centigrade. Just I'm trying to give the concept. Nobody will ask in that much of detail in interview, but as an engineer you should be aware of this. In interview they may ask the formula. So C equal to F minus 32 by 1.8. Getting a point online?
Yes.
Now similarly, F equal to what? 1.8 C plus 32, because here we are subtracting, here we are adding, here we are dividing, here we are multiplying, because this Fahrenheit is 1.8 division, no? So we need to increase that division. Okay, and 32 we are adding. But remember, this is for temperature to temperature conversion. Remember, in case if you are converting this temperature difference, in case of temperature difference, this 32 factor is not applicable. For example, you see 30 degrees centigrade minus 20 degrees centigrade. This is what? 10 degrees centigrade. Na? This 10 degrees centigrade, if I convert this with this formula, you see 10 degrees centigrade. Na? So F equal to 1.8 C plus 32. Can you please calculate this? 1.8 multiply with 10 plus 32. Can you please do it?
50.
This is 50 degree Fahrenheit. So this is going to be a big wrong. Here 10 degree centigrade in terms of Fahrenheit is 50. There is no confusion in this. But why I'm saying this is wrong? Because this 10 degree centigrade is not a temperature on the scale. No? This is a difference of these two temperatures. So in that case, the starting point is not applicable. This stuff difference 32.
I don't. Please repeat it.
You see, if I say the room temperature say 10 degrees centigrade, in that case you can say it's 50 degree Fahrenheit. That's correct, because you see 10 degree in this is 50 degree Fahrenheit. But if I say the difference of the two rooms, for example, room 1 and room 2, room 1 said 30 degrees centigrade and room 2 said 20 degrees centigrade. So the difference of these two, delta T, is what? 10 degrees centigrade. So this 10 degrees centigrade is not a temperature of the space, no? It's a difference of the two temperatures. So for difference, you see this starting difference 0 and 32, this difference is not applicable. We need to consider only the division difference. The division is what? 1 equal to 1.8. 1 degree centigrade is equal to 1.8 degree Fahrenheit. This is very, very important. At the time of load calculation also we'll use this. So remember, if you want to convert temperature to temperature, one can use this formula. C equal to F minus 32 by 1.8 or F equal to 1.8 multiply with C plus 32. No confusion. But in case if you want to convert this temperature difference, in that case, you see here, F by 1.8. 32 is not in this formula. Similarly, F equal to 1.8 C plus 32 is not applicable in this. So this is for what? This is for temperature difference. So remember, when you are converting a temperature, use this formula. When you want to convert temperature difference, then 32 is not applicable. You can use these formulas. Very, very important. Clear online? Very basic and important. We'll use this at the time of load calculation. And you see, now if I use this conversion, suppose 10 degrees centigrade is a what? Delta T, temperature difference. Na? So now if you use to convert into centigrade, then 1.8 into 10. This is going to be 18.9. Say round off to 19 degree Fahrenheit. So previously we got 50 degree Fahrenheit. Now we got 19 degree Fahrenheit. You see the difference is more than double.
So why it's 18.9 should be 18?
0.9, na? Above 0.5, we are taking higher value. Below 0.5, we're taking lower value. Okay.
No, sir. 1.8 into 10, na? It's 18. 1.8 into 10. So 10 degrees Celsius.
Okay, sorry, my mistake. So consider 18. Okay. So you see, previously it was 50, now it's 18. So you see the difference is more than what? Double. So got the idea online? The importance of this temperature in the temperature scale formulas. Or is what we can do, one can convert this into Kelvin, then you can use the conversion. But the end result is going to be same. So we have a direct formulas. Okay, so whatever, if you have any other technique or if you want to convert both into Kelvin from the 0, you can do that one, but it will be a lengthy process. So we have this direct formulas for temperature and temperature difference. Clear online? Next, you see I've given the note also at minus 40, the difference between both the scale will be 0. Next, we have one more very important unit of refrigeration. And unit of refrigeration is what in actual practice? Did you heard the term ton?
PR, tonnage.
See, so don't get confused. One is a TON. TON is what? 1000 kg. We used to call 1000 kg is 1 ton. That is related to weight. But if I use the unit of refrigeration, I used to write TR. But we have a relation between these two, this ton and this ton. So how exactly we'll discuss. So first, this is weight and this is a cooling capacity or unit of refrigeration. So how exactly we got this, we'll try to understand. Let me read the definition first. You see, 1 ton of refrigeration is defined as the amount of heat energy required to melt 1 ton, nothing but 1000 kg in terms of pound is 2204, nearly 2000 pounds of ice. Or if you're getting confusion in pounds, just consider 1000 kg. Okay, so it's the amount of heat energy required to melt, say 1000 kg of ice at what? 0 degree centigrade, nothing but 32 degree Fahrenheit in water at constant temperature. In what time? Say 24 hours. We're considering this time for calculation point of view. So, okay, try to understand this. For example, consider this as say 1 ton of ice, nothing but 1000 kg. And ignore the sun. Assume that this is a room. This 1000 kg of ice I purchased from somewhere and I place in this room. And I'm going to close the door. So after 24 hours, again when I enter in the room, this ice, this solid will change to liquid, na? And why it will change from solid to liquid?
Gain.
Because extraction of heat, na? But extraction of heat from where?
Room.
Yes, from the room. So when you enter into the room, what do you think? The room temperature will be same as before 24 hours, or it will drop?
It will drop.
It will drop, right? Because extraction of heat, because of melting of ice. And when you enter in the room, you'll feel the cooling effect. So that cooling effect we can call as 1 ton of refrigeration. Or technically, the cooling effect produced by melting of 1000 kg of ice. Say in 24 hours, we are considering time calculation point of view. So the cooling effect produced by melting of 1000 kg of ice is 1 ton of refrigeration. So this 1000 kg is ton. With that, we are getting the cooling effect. So we are calling 1 TR. So both are interrelated but different. Because of this ton, we are getting this ton. Because of this ton weight, we are getting this cooling effect. So we used to call the pronunciation is same, but the concept is different. Very simple. Got the idea online? So technically, we'll try to define this. Theoretical, I think you got the idea. It's simple. When you melt 1000 kg of ice, the cooling effect produced by melting of that ice, because you see melting of that ice required heat. With the extraction of heat, then only it will melt. Okay, so that extraction of heat is equal to 1 ton of refrigeration. Nothing but 1 TR. And this is commonly used in the HVAC industry. I think you already heard this ton of refrigeration, very commonly used. One can use the kilowatt also for this capacity. But for cooling point of view, especially not for heating, for cooling point of view, we are using this ton, 1 ton or 2 ton split AC, window AC, or 100 TR chiller, etc. Now we'll try to define this mathematically. See, simple. The latent heat of ice. But I think you have not discussed this latent heat. No? In the next pages only, you'll find the sensible and latent heat. At this level, remember, latent heat means the heat because of change of phase. In short, sensible is what? Okay, we'll discuss about sensible latent in the next page. At this level, just remember, latent heat means the heat because of change in phase. So in this case, the ice is melting to water, na? So change of phase. So because of change of phase, the heat is added or removed. That type of heat is called latent heat at this level. Okay, we'll discuss more about this in this chapter only. So you see, based on the experiment, we have this value. The latent heat of ice is what? 335 kilojoules per kg. Means for 1 kg of ice, if you want to melt, you need to provide how much of heat? 335 kilojoules. Kilojoules also unit of heat, na? In 24 hours. For example, we are considering for calculation. So therefore, 1 TR equal to what? 335 multiply with 1000 kg. In terms of this timing point of view, 335 multiply with 1000 divide with 24 into 60. Why 60? Because I want result in minutes. For example, commonly we are using this. So the result is what? 232.6 kilojoules per minute. In actual practice, considering the losses and other assumptions or other condition, we are considering this value as standard, 210 kilojoules per minute. 110 equal to 210 kilojoules per minute. So what you are getting with this? It means, for example, consider this is a room. In this room, if you want to produce 1 ton of cooling effect, what can be the rate of heat extraction?
210 kilojoules per minute.
Kilojoules means if you are using any equipment here in this room, and if you want 1 ton of cooling effect in the space, the rate of extraction should be 210 kilojoules per minute. So if you extract the heat with a rate of 210 kilojoules per minute, one can expect what? 1 ton of cooling. Similarly, if you want 2 ton of cooling, then yes,
one basic question is that if we set the temperature in different degrees Celsius, for 20 degrees Celsius, or maybe 22 degrees Celsius,
you see that will do in the load calculation. What temperature, according to that, what in order to maintain the temperature, what will be the tonnage required, what will be the rate of heat extraction, etc. Okay, so I got your point, but at this level, I'm not talking about the load calculation. Just means the cooling effect. You see, what we learn is 1 ton of cooling effect is what? When you melt 1000 kg of ice. So the cooling effect produced by 1000 kg of ice is 1 ton. So same, if you want to produce the cooling effect which is produced by melting 1000 kg of ice. The same if you want to produce with the equipment, say cooling equipment, the cooling equipment rate of heat extraction should be
210 kilojoules.
right, 210 kilojoules per minute. Okay, so what you're asking, I'm getting this, but don't go in that load calculation. For that we have a detailed procedure. So at this level, the rate of heat extraction to get 1 ton of cooling effect. But how much cooling effect, or what will be the rate of heat extraction to maintain the temperature, that need a list of sources to verify, and we require detailed calculation. So we'll get what will be the rate of heat extraction to maintain the temperature to get that cooling effect. So at this level, simply 1 ton equal to what? 210 kilojoules per minute. In terms of BTU, we have 12,000 BTU per hour. It means if you want to produce 1 ton of cooling effect in a space, the rate of extraction should be 12,000 BTU per hour.
So one question is that we're saying that this machine is 1 tier capacity. This machine has the capacity to extract the heat of 210 kilojoule per minute. That is maximum capacity. We can alternately say that. Okay.
Yes, and you see, if the rate of heat gain is more than that, we cannot maintain the temperature. If the rate of heat gain is less than that, one can maintain the temperature. So that we'll discuss. We have a topic detail in load calculation. To maintain the temperature, that should be balanced, na? Q in should be equal to Q out. So at this level, just we are learning the concept of the capacity of the cooling. So see, in terms of BTU, this is also important for interview point of view. 1 ton equal to 12,000 BTU per hour. In terms of kilowatt, it's 3.5 kilowatt. And this kilowatt is not an electrical kilowatt. Remember, it's a mechanical kilowatt. Heat. Okay, so don't get confused. So remember, for example, if I consider 1 ton split AC, 1 ton split AC means it can extract 3.5 kilowatt heat, and this kilowatt is a mechanical. And for that, electrical kilowatt can be 1.2 to 1.4 kilowatt. That is electrical consumption. So electrical kilowatt is different, mechanical kilowatt is different. So this is mechanical kilowatt, not electrical kilowatt. Remember this. We'll use at the time of calculation. You may not get the idea at this level, but remember, this is not electrical kilowatt. This is a mechanical kilowatt, 3.5. And it's a fix. It will not change. Electrical kilowatt may vary based as per the efficiency of the equipment. Okay. So we have a range from 0.8 to 1.5 kilowatt per ton for electrical side. But that depends on the efficiency and other factor. But this is fixed. This is a conversion.
For 1 tonnage machine, how much electrical capacity required?
0.8 to 1.5 in between. That depends on the efficiency. But don't write. We'll discuss this at the time of machine selection. Or for interview point of view, you can consider 1.2 to 1.4 if you talk about split. In case of chiller, the case is different. The chiller start with 0.7. Again, in that chiller, we have a different high-class chiller or a standard chiller, etc. So that range will vary.
Yes, sir. For coordination point of view,
1.2 to 1.4.
Yeah, because electrical engineer is always asking about the electrical load of the HVAC.
You can consider in between 1.2 to 1.4 for a DX system. For chill water system, is going to be different. Next, so I think got the idea. What is the ton of refrigeration online? Next, we'll talk about enthalpy. So we start this chapter 3 with the heat only, no? So enthalpy is nothing but heat. Just where we will learn in a technical way. Okay, so you see, enthalpy is what? It's the sum of internal energy U and the product of pressure and the volume. And in short, we used to call H enthalpy H equal to U plus PV. And as the pressure increases, what will happen to the temperature? Or if the temperature increases, what will happen to the pressure?
Pressure will increase.
Yes, both are directly proportional, right? And when you add the energy, that is a heat, so what will happen? Pressure increases. As the pressure increases, the temperature also increases. And remember, this relation we'll use at the time of vapor compression cycle, because at the time of compression in a compressor, the temperature and pressure both will increase, but the volume decreases. That we'll discuss. So remember this, very basic, you see. Or in other words, you can say enthalpy is what? Heat transfer at constant pressure. Or practical or application point of view, heat content of the body is called enthalpy. This is a practical definition for interview point of view. Remember, enthalpy is what? Heat content of the body. Nothing but heat energy or heat. Okay. So that can be measured in kilojoules per hour or BTU, what we discussed at the beginning of this chapter 3. This example will help. You see, here inside, suppose a gas, and we are adding the heat. So what will happen? Adding the heat means we are increasing the internal energy. Adding the heat is a form of energy, no? So what will happen? You see, the piston will go up because the pressure and the the temperature increases. So, and because of this, it will push up and the volume also increases. Okay, this concept will use at the time of vapor compression cycle. Remember, it's very, very important, because in vapor compression cycle, if you talk about the actual side, you'll find the different pipe sizes for liquid and for this suction, means for gas. So H equal to U plus PV is the equation for enthalpy. Just remember this, we'll use at the time of calculation. Next, this is also very, very basic and important, sensible and latent heat. So first of all, I'll give you the idea why this is important, so that you can get the interest and we can try to understand this type of heat. So why this sensible latent is important? Remember, at the time of load calculation, when we deal with the different sources of heat gain or heat loss, heat gain in summer and heat loss in winter, first we'll find out the different sources of heat gain or heat loss as per the requirement. For example, at this level, I take example of cooling system in summer. So in cooling system for summer, we are interested to calculate heat gain, and for heat gain, we'll find out the sources first. I'll give you a few example. We have a list in chapter 7 in detail. At this level, just for example, heat gain through wall is one source. Heat gain through glass, nothing but window, or heat gain through partition, floor, ceiling, or ventilation, infiltration. Like this, you'll have people, lighting appliances. We have a complete list. So remember, at the time when we deal with the heat gain through these different sources, first you must know that heat gain is only sensible or sensible plus latent. According to that, we have a formulas. For example, heat gain through wall. Remember, it's only sensible. But what is sensible, we have not discussed yet. We'll discuss, don't worry. Just I'm trying to give the importance of this topic. Similarly, heat gain through ventilation is not just sensible, it's a sensible plus latent. Okay, because the moisture also involved in that. Similarly, heat gain through people is a sensible plus latent. So what is exactly the sensible latent? We'll discuss now. First of all, some theory. You see, sensibility refers to what? Heat energy that causes change in temperature of a substance without changing its state. Remember, adding or extracting the heat without change in phase is a sensible heat. For example, if we take a container filled with water and adding the heat, so what will happen?
Starts to boil.
It will start to boil, but after some time, no? Not quickly. Starting, for example, this is at 0 degrees centigrade. Sorry, 0 degrees centigrade. So it will increase the temperature to 1, 2, 3, 4, 5, up to what? Up to 100. Then at 100, it start changing its phase. So heat, adding heat from say 0 degree to 100 degree is what? Without changing its phase, na? It's a sensibility. Or reverse. For example, this water at 99 degrees centigrade and I'm extracting the heat from 99 to 0 without changing a phase. Is a sensible, right? So simple. Sensible is what? Adding or extracting the heat without changing its state with the same condition. Okay, for example, ice at say minus 10 degrees centigrade. Suppose this ice at minus 10 degrees centigrade. I'm adding the heat. So what will happen? Yes, online?
Temperature will increase.
Just temperature will increase, it will not start melting. When it will start melting? At when the temperature is to 0 degrees centigrade. So minus 10 to say minus 9, adding the heat. That heat is what?
Sensible.
Sensible. Simple, right? It can be solid, it can be liquid, or it can be in vapor. Suppose vapor means above 100 degrees centigrade and adding the heat. So the vapor in the vapor only, and it will increase the heat to say 101, 102, etc. So again, that is a sensible. So remember, adding or extracting the heat without change in phase is called a sensible heat. For example, heat gain through wall from outside to inside. Is there any change in phase? Or is there any moisture traveling from outside to inside? No. So we can consider the heat gain through wall. I'm just talking about the application side. The heat gain through wall is what? Only sensible. But if the heat, okay, so next we'll talk about latent, then we'll take more example. Let me quickly complete this theory. So you see, sensible heat refers to the heat that causes a change in temperature of a substance without changing its state. In other words, it's a heat energy that can be felt or sensed in general, as it leads to a noticeable change in the substance temperature. Okay. So when the sensible heat is added to a metal, its temperature increases, and when sensible heat is removed, the metal temperature decreases. Sensible heat transfer is common in every situation, such as when you feel warm of sunlight or the skin, or a colder on a breeze, etc. Just a feeling, sensible feeling without any change in phase. We are not getting the sweat. Just we are feeling hot or cold without any getting sweat. So if involved in moisture or change of phase, means that comes under the next latent. We'll discuss. Let me complete the sensible first. So if you talk about sensible, we have this equation Q equal to mCp delta T. We'll use at the time of calculation. This is a very general formula. Later at the time of calculation, you'll find UA delta T, some modified formulas, but this is a general formula mCp delta T. So here Q is a sensible heat in this case because we are talking about sensible. Say BTU, or it can be joules or kilojoules. M is the mass of the substance. In case of say flow rate of air, we are using CFM, or in case of any solid, say pound or kg. C is a specific heat of that substance. And remember, the specific heat of the substance depend from substance to substance. Specific heat of water is different compared with the air, or the specific heat of milk is different compared with the any other fluid. Okay, so that you'll get from the table. And delta T is a change in temperature from the two side of that body. Okay, so just remember this formula. When we deal with the load calculation, you'll find the modified formulas, and we'll discuss in with more detail. At this level, I'm not just going in detail for this formula. Just I'm defining mCp delta T. What is what? Next. So same example, heat gain through wall, heat gain through glass, etc. We can consider as a sensible. And this is very, very important. Throughout the load calculation, when we deal with all possible sources, we'll check whether the source is conduction, convection, radiation, or only conduction, or it's a mixed mode, plus whether it's a sensible only or sensible plus latent. According to that, we have a calculation. Okay, so very, very basic to deal with the manual load calculation. Manual load calculation you can consider as a basic for the software load calculation. So it's a process. Okay, next we'll talk about the latent heat. Simple. You see, latent heat refers to the heat energy absorbed or released during a phase change of a substance, such as melting or boiling. For example, consider the same case. A container with the water. I'm adding the heat. Suppose initial temperature is 0 degrees centigrade, and that reaches to 100 degrees centigrade now. So what happened at 100 degrees centigrade? Further, the temperature will not increase because the boiling point of water is 100 degrees. But still I'm adding the heat. So where that heat goes?
Phase change.
Yes, that heat is utilized to change the phase. And that heat is called latent heat. So remember, sensible heat means adding or extracting the heat without change of phase, but the temperature will change. But remember, latent heat means at constant temperature, change of phase. When you continuously add the heat is a latent. So the important point is, first point is latent heat means this is for change of phase from solid to liquid, from liquid to vapor, or vice versa. And the second important point, whenever the starting to end change of phase, the temperature is going to be constant. At 100 degree only the starting of vaporization, and at that temperature only complete water will convert to vapor. Or for example, if you take a ice at 0 degree centigrade and adding the heat, what will happen? Start melting at 0 degree. Till the completion of melting, it's going to be at 0 degree only. And after that change of phase into liquid, then further if you had, it increase the temperature to 1 degree, 2 degree, etc. up to 100. Again at 100, it's going to be constant till the conversion process from liquid to vapor. Okay, so latent heat means this is related to change of phase, and second point is at constant temperature. You see, latent heat refers to the heat energy absorbed or released during a phase change of a substance, such as melting, vaporizing, or condensation. Vaporizing means vapor to liquid. Condensation means, sorry, my mistake. Vaporizing means liquid to vapor, and condensation means vapor to liquid, reverse. So it is important to note that during a phase change, the temperature of the substance remain constant, even though the heat is added or removed. Okay, so this is very important, and this concept will also use at the time of vapor compression cycle. You see, when the change of phase from vapor to liquid in condenser, because of rejection of heat equal to latent heat at constant temperature. Similarly, change of phase from liquid to vapor in evaporator because of extracting the heat equal to latent heat at constant temperature again. So this concept, sensible latent, first we'll use in vapor conversion cycle, then we'll also use in load calculation. Because if you talk about load calculation, one example, heat gain through ventilation. What do you think? Is it only sensible or sensible plus latent or only latent?
Sensible plus latent.
Yes, sensible plus latent. Why sensible plus latent? Because heat gain through ventilation means outside air. And remember, air means what?
Fluid.
Fluid. But with respect to psychometric.
Dryer plus moisture.
Yes, it's air means, if I use the term air means, by default I'm talking about the moisture. The moisture means dry air. Dry air refers to the sensible and the moisture is refers to the latent, because that moisture we need to extract and condense on the cooling coil to decrease that humidity level in the space. So that condensation is required. So the change of phase, and that change of phase means that the moisture inside the space, you're going to condense on the cooling coil. Again, that change of phase comes at a latent. Okay, so this sensible latent will use throughout the load calculation. Okay, as per this type of source. Yeah, so the same, you will find the formula also for this latent. You see Q equal to ml. So where Q is latent heat here, and m is a mass, and L is a latent heat of the substance. And this latent heat of the substance you'll get from the table, like 335 kilojoules per kg for ice. Similarly, for different substance, you'll find this value that we'll use at the time of load calculation. So this level, just memorize this formula. The application side, you'll find the modifiers formulas as per the source of heat gain. Further, if you talk about this latent heat, as I said, this change of phase, the change of phase can be liquid to vapor, or can be this, can be solid to the liquid, and can be this liquid to the vapor. So you see, this is divided into two. First is a latent heat of fusion. Fusion means what? Solid to liquid. This different term is given. If the change of phase from solid to liquid, we used to call latent heat of fusion. If it is from liquid to gas, we used to call latent heat of vaporization. Next, for learning point of view, here you see application point of view, heat gain through ventilation in filtration people is the example of sensible plus latent. Remember, the source can be only sensible or can be sensible plus latent. We don't have an option for only latent in case of source of heat gain. Okay. So in this table or in this figure, you can find increase in X direction is a heat content, nothing but enthalpy. And in Y direction, you can consider temperature in degree centigrade as well as in degree Fahrenheit. And this line represents the state of, say, water, this blue color line. Okay, starting from here. So now you can notice at 32 degree Fahrenheit or 0 degree centigrade, the state of water. I'm considering example as water. So the state of water is what? Solid or liquid?
Solid.
1 minute. Yeah, solid, right? And now below that temperature, below the 0 degree, suppose if I consider this, say, minus 17.8, so solid. Okay, you see 0 degree Fahrenheit or minus 17.8 degree centigrade. This is solid. So you see, thus adding, just for example, assume that I'm adding heat to this solid, nothing but ice. So what will happen? Slowly the temperature increases and the heat also added. But you see, this solid is going to be in solid only. But at this point, which is melting temperature or the freezing temperature of water, after this temperature, further if you add the heat, what will happen?
Phase change.
The conversion process start. It means, you see, this phase can I consider as sensible? No change in phase now. Adding the heat and increasing the temperature, but no change in phase. But at 32 degree Fahrenheit or 0 degree centigrade, further if you add the heat, what will happen? The conversion process start. Means the melting of start from point 2, and the complete melting is done at point 3. So this phase is, or this heat is called what? Latent heat. And this 144 BTU is for what? I'm considering 1 pound of water. So it means for 1 pound of water, if you want to convert from solid to liquid, how much heat amount is required in terms of BTU? 144. In metric system, you'll find the different values. This is English system, 144 BTU. It means when you add 144 BTU in 1 pound of ice, that will convert to water. So this much of heat energy is required based on the experiment. Okay. So 0.223 is what? Latent. Means change of phase. And now you can notice that change of phase, the line is horizontal. Is there any increase in vertical? No, it means, you know, this is a proof na, this change of phase at what? At constant temperature. This is an important point. That's the reason I'm showing this. So the change of phase at constant temperature. So if you are adding the heat, but that heat is not utilizing to increase the temperature, that is used to change the phase. So now at 0.3, it's completely in liquid. Further, if you add the heat, what will happen?
Rise of temperature.
What will happen? The temperature increases. Temperature also increases. Na? So you see 0.3 to 0.4, you can consider increase in temperature without changing of phase. And you can notice this inclined line. Na? Inclined line means increase in temperature as well as in heat. In case of latent, the temperature will not increase, but in case of sensible, the temperature increases, adding the heat. Okay, so here inclined line represent what? Sensible. And how much BTUs are required? 180 BTUs required in order to means heat up that water up to what? Up to the boiling point. And you know, 200, this 212 degree Fahrenheit or 100 degree centigrade is what? Is a boiling point of water. No? So at this point, now the water is ready to evaporate. So this phase we can consider as sensible because adding the heat will increase the temperature without changing phase. Next at 0.4, further if you add the heat, what will happen? The temperature will not increase. The change of phase start. Again change of phase start, you can see 4.4 to 5. There is no change in the temperature. So you know, it's a latent heat. And as per the experiment, we have this 970 BTU. If you add that heat, so the complete water can vaporize to liquid. And the amount of water is, for calculation point of view, are considering as 1 pound. Now at 0.4, the state of water is what? It is completely in gas. It is in vapor. Na? Further, if you add the heat, what will happen? The temperature of the vapor increases. We can call, say, superheated steam or superheated gas. So you see at 0.5, completely it is in vapor state, means gas state. Further, if you add the heat, gas, the vapor in the vapor state only is in the gas state, but the temperature increases. Again, that we can call as a sensible. And why I'm focusing on this topic? Because at the time of vapor compression cycle, we'll use all this information. Because in vapor compression cycle, at the time of condensation, release the rejection of heat equal to latent heat, then only the change of phase. And at the time of evaporation in evaporator, again extraction of heat equal to latent heat, then only the change of phase will happen. Okay, so that's the reason this topic is important. And based on the vapor compression cycle only, we have this chapter 5. This classification of machines means the classification of air conditioners, different air conditioning, and works on the vapor compression cycle. If we talk about all commercial and residential air conditioning systems, that works on VCR, means vapor compression cycle. We have vapor absorption, we have this Trolux, or we have this air system, different cycle in actual practice, but most commonly in actual practice for commercial and residential air conditioning system, including the refrigeration, you'll find VCR. Okay.
Just 1 minute, sir.
Yes.
How it is related to the vapor compression cycle, this latent heat and this?
I've given the example in the condenser, change of phase, right? If you already know, you can relate. If someone don't know, don't worry. We have a separate topic in detail for vapor compression cycle. In vapor compression cycle, we have this condenser as well as evaporator, and both are heat exchanger. Na? So in condenser, what will happen? The change of phase from this gas to liquid. And whenever change of phase means that substance must reject the heat equal to latent heat. Okay. So in that sense, this is important for vapor compression cycle. Similarly for evaporator side also, the case is same but reverse. Extraction of heat and change of phase from liquid to vapor. Again, by extracting the heat equal to latent heat.
Okay. That means in condenser, no temperature of rise, only phase change will occur, right?
Yes, at the time of rejection of heat equal to latent, means in case of change of phase means the temperature is going to be same. But don't worry, I'll explain in detail about vapor cycle. We have a detailed topic, if possible today only. If not, we'll deal with in the next session. Because without that, you cannot think for this classification of air conditioning. Even in chill water, in chillers, you'll find a vapor compression cycle. You have vapor absorption cycle, vapor absorption chillers also. Commonly in actual practice, the compact type compared to vapor absorption is a vapor compression cycle chillers. We have topic in detail. So at this level, just focus on this topic so that we can use at the time of vapor compression cycle. Okay. So got the idea online about this sensible and latent heat.